about 2000, they're down to 1/10,000th of a millimeter and decreasing fast. Pretty soon we're going to have nano machines. We already have micro machines, like that device that you're working on.
Well, there's one in here. There's a micro mirror device in this DLP projector.
Oh, cool.
There are 1 million mirrors that are wiggling right now.
1 million mirrors wiggling to show us this picture. Huh? That's really cool. So that's a micro machine. And pretty soon we'll have nano machines that have features that are 1,000 or 10,000 times smaller than that. So the rate of change in the size of the machines that we're able to create is also increasing. Because you see, this is also a logarithmic scale. It goes from 0.1, 0.01, 0.001, and so on. Powers of 10. And yet the curve is curved. That means it's another double exponential curve. And you can look at almost any industry, any human endeavor, any area of pure research, and especially in the technology area, and you'll see the same thing. Like I said, I have a whole folder full of these charts that show similar double exponential curves in various areas. So what's going on? Let's look at another. What is the anatomy of this level of change? Oops. Well, let's go back. Yeah. What's happening is that there are a whole bunch of little changes making these big changes. This curve shows the adoption of a particular technology. A means we got a new capability that we didn't have before. And then that's rolled out into applications. And at B, we are able to integrate that new application or that new capability with existing applications. At that point, the rate of change begins to take off. At C, at the top of the curve, means we reach the ultimate potential or the limit of development of that technology. And at D, it means the use of the technology is declining, usually because we found something new and better to replace it. So what happens when you are looking at a particular technology? Let's take data storage, for example. Over time, the first wave might be, for example, filing cabinets. And then somebody came up with perforated paper and binders. And that enabled us to increase the density of our data storage. And then somebody came up with the phonograph. And all of a sudden we can store a lot of data on a little phonograph record. And then somebody else comes up with the optical discs. And then somebody else comes up with a hard drive. Remember the first hard drives? They were the size of a refrigerator and they held a whopping 10 megabytes. Now 10 megabytes will fit on a microscopic chip. You can't even hardly see it. It's just about the size of a grain of dust. So each successive technology drives the curve faster and faster because of the integration factor. It integrates with the previous technologies and increases their efficiency. So like every new generation of technological change drives the rate of change itself faster and faster. This cycle takes place in a shorter and shorter time span and becomes more and more efficient because it builds on the existing infrastructure of other devices that are also going through the same technological change. Like this projector technology he was talking about, it couldn't exist without so many other technologies like large-scale chip integration and nanofabrication and so many other things, lithography and so on, that didn't exist 10 years ago. So because those things are improving rapidly, then these other things based on it can improve rapidly, and it leverages the amount of change, increasing it faster and faster. So now this is happening all over the world in so many different areas that the rate of change in general in society is speeding up. Now let me show you the time wave. And this is going to look real familiar, because guess what? It's a double exponential curve. The bottom scale here is time, all time. And this vertical scale is change. So basically this is telling the same story, even though, you know, it's got a little noise and stuff in it, but still it's basically a double exponential curve. This is an exponential graph. Each line here is 10 times the amount of change of the previous value. And this time axis here is linear. So along the time axis we see there are periods where there's relatively little change, or the rate of change remains constant for a long time. And then we gradually come along till we reach a certain area here, then things start to get really volatile. The rate of change itself is changing quite rapidly, and then finally the rate of change just takes off and goes right through the roof. So where are we on this graph? Right here. This is the year 2008. If we were to zoom in on this area right here, guess what we would see? Approximately the same picture. This little area, this little glitch right here, if you expand it out, it's like the same curve starting from about right here. Why? Because time is fractal. A fractal means when you zoom into it, it looks exactly the same or similar. The design, the curve, the whole thing looks pretty much just like you would see it at the large scale. Is everybody cool with that concept? I have a bunch of pictures I could show to explain it, but if you're already...
Could you expand a little bit on time wave zero? Maybe some people don't know what that is.
So like, how did we get this?
Yes, what is the data that you use to extrapolate that information?
Okay, this was developed by Terence McKenna, a research partner of mine. We did a lot of research into the Vedic Soma. And basically what he did was he took the, well, it was based on the Mayan calendar, and it's also based on the I Ching. He took the I Ching and analyzed it as a calendar. What would happen? You know, the I Ching is about change, right? And it's a series of 64 hexagrams. And each of these hexagrams has a certain significance, a certain meaning. And then it changes into the next one. So you can very easily calculate the degree of change that occurs between one hexagram and the next. So he did that using a particular classical sequence of hexagrams called the King-Wen system. So the King-Wen system, or the King-Wen series of hexagrams, involves all these changes, and he statistically analyzed the degree of change, or the amount of change, between one hexagram and the next. And this is the curve he came up with. It's called the time wave. And like I said, it's fractal. You can zoom in on any particular detail part of this curve, and it'll have approximately the same shape as the entire curve. Yes, Ben?
Was this his theory on novelty?
Yes, the theory of novelty.
Okay, and does this have anything to do with the Fibonacci spiral?
Well,
He mentioned that
there's some mathematical relationship between them.
But not quite the same.
Not exactly the same,
Okay.
no. But really what you have here is another one of those double exponential curves.
Is there a book about this, or that one could refer to, or is it
There's quite a few websites, and there's a couple of sites where you can download the software that generates this. that allows you to zoom in on it and examine specific areas, specific dates. And it's so amazing the correlation between the places on this curve and specific dates such as like the French Revolution, the World Wars, you know, different historical occurrences.
So what should we Google for? Time wave zero?
Terence McKenna.
Time Wave Zero, Terence McKenna.
Okay.
Yeah.
Bob, I'm sorry, one question.
I can't see.
Oh, one question. Can you apply this software to your personal astrology? Can you plug in data sets personally to analyze peaks and...
I suppose you could, yeah. You would take a lot of work, a lot of customizing.
Oh, I was wondering if
It's much easier to use the planetary periods, which in Vedic astrology serve the same purpose.
Okay.
We can go over that tomorrow.
Great.
Keep that in mind, okay?
Oh, absolutely.
Okay.
This is great.
Yeah, we'll look into it tomorrow when we do Vedic astrology.